Okay, the next thing we're going to look at is Dalton's law of partial pressures. And all this says is really not anything new. It's just that the total pressure is the sum of all the partial pressures of the gases. And I even think some of the worksheets had a couple of problems on this, because all you have to do is talk about the pressure of the gas, whatever gas you're talking about, as if it were the only gas in the container, and that's its partial pressure. So it's the gas that's responsible for hitting the walls of the container and causing the pressure from that particular gas. So if I look at the total pressure in a container, I can say, well, maybe some of that molecules hitting the sides of the container is oxygen, some of it maybe is helium, some of it's nitrogen, whatever's in that container. And then together, all three of those different gases hitting the sides of the container come up with the total pressure. So we can monkey around with this with PV equals nRT. And what we find is that we can find the total pressure by taking the total number of moles times that constant R times the temperature in Kelvin divided by volume. But we're just going to use PV equals nRT in this problem as well. We're just going to focus on different gases. So to get a visual on this, and that's really quite important to do that, you can think of gas A here and gas B here, and we've got a pressure, we've got a pressure. Well, together, when they're together like this, you can see some of the red ones are hitting. They're going to contribute this 1 atmosphere of pressure. The blue is going to contribute 3 atmospheres of pressure for a grand total of 4. And you can use PV equals nRT for this gas, PV equals nRT for that gas, and then you could use PV equals nRT for this as well. You just have to use both of the blue and the red in your N value there. All right. So because of that, you can talk about this mole fraction, and this is one way that you can talk about the problem and do the problem. You don't have to do it this way. You can always, well, depending on the information that's given to you, you can use PV equals nRT. If you don't have enough information to do that, you can always realize that, look, the total pressure of the gas, or the pressure of the gas that you're looking for, like say oxygen, in a mixture of oxygen and nitrogen and argon and whatnot. If I'm looking for just that pressure, I could take the total pressure in the container and multiply it by just the fraction of the gas I'm looking for. So I would take all of the gases like argon, nitrogen, oxygen, and all that. And let's say I'm just looking for oxygen. Well, then I put the moles of oxygen up here, the total moles down here, multiply by the total pressure, and then I get the pressure of just that gas. So the other thing about this is, and we're going to talk about this more in the kinetic molecular theory, is that it's not going to matter what kind of gas we're looking at here. It's every gas molecule is considered to actually be no volume, which we'll talk about later. But so we're only going to focus on moles, not what size the molecule or the type of gas it is. All right. So as an example here, we've got a 2-liter flask. Contains 0.05 moles of nitrogen and an unknown amount of oxygen at 25 degrees Celsius. The total pressure is 0.91. So obviously some of that is contributed to the nitrogen and some of it to the oxygen. So we want to know the partial pressure of each container and of each gas in the container. Now there are a couple different ways you could do this, but I will take a look at just looking at the pressure of nitrogen because I know it's in a 2-liter container, and that 2-liter container contains both of these things. So 2 liters is the space available to the nitrogen. I have, actually that should be 0.05 times 0.081 times 298. When you calculate this, you should get the pressure of just the nitrogen at 0.61. Okay, I'm just going to make sure that's right. Yep, 0.61. Okay, even though that should be a 0.05 there. Then, because both of those gases are in there, the remainder of it must be the pressure of the oxygen. All right, let's take another look, and you might have even done this problem. We are going to take 4 grams of each gas, and we are going to convert this. Now, be sure when you're converting a diatomic, and this will be a real interesting case of seeing who remembers to do diatomics. Helium is not a diatomic. If you look at your periodic table, it's 4 grams per mole. And so when I convert this, I'm going to get 1 mole of helium. Fluorine is diatomic. I will not use 19 here. I'll use 38. Remember your diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, iodine, bromine. I'm going to divide, I'll get 0.105 moles of fluorine. So if I want to do the pressure of just a helium, I'll take the total pressure, which I have 3 atmospheres. I will take this mole fraction, and if it's helium, I've got 1 mole of helium here. And the total number, right there, and then the total number of these two is 1.105. So I'm taking the mole fraction, just the helium, times the total pressure, and I'm going to get the pressure of just the helium. The remainder then that, the 0.3 then, 3 atmospheres is the total pressure. 3 minus 2.7 is going to give us 0.3, and so that would be the pressure of the fluorine. Now, this comes into play quite often when we are collecting a gas over water, and if we were in class, we would be doing a lab on this. It happens at any temperature. We talked about vapor pressure in chapter 14. What happens at any temperature, the warmer it is, the more it is, of course, but some of the water molecules are going to break free from those intermolecular forces. They're going to go into the gas state, and they're going to be there. And when we're trying to collect a gas, I'll show you a picture here, that gets in the way. We don't want that water vapor. We want to collect, say, oxygen, or we want to collect helium, or whatever we want to collect. The water vapor is in the way. So we're going to use this next chart here, and I would print it out for you, but unfortunately we're not together here this year, so you will have to refer back to this. But we're going to subtract the water vapor pressure at a given temperature from the total pressure to get what's called the pressure of the dry gas alone. So as we see here, let's say that we're running this temperature at 22 degrees Celsius, which is pretty common. I would have to take the pressure that I measure, whatever pressure I'm measuring, and I'd have to subtract 19.8 from it to get rid of the water. And that's torr or millimeters of mercury, it's the same thing. I would subtract that away from the total pressure, and then that would give me the pressure of just the dry gas. So whatever temperature you're looking at, and if it's collected over water, come back here. I'll try to highlight or bold over water so you know to come back here, look at the temperature subtracted out. So let's take a look. So this is a common reaction. We're running something, we've got a tube. We collect it underwater. This was full of water, but as it bubbles, the gas bubbles up, the water gets pushed out. We collect this gas, we make it even with the water level outside, then we're able to tell it's the same as the atmospheric pressure. Pressure outside is the same as the pressure inside. So we're able to measure the pressure, but then what we have to do is we have to subtract out the water vapor pressure to just get the dry pressure here of the gas we're collecting. And so I have an example here where I'm going to heat some potassium chlorate. Oxygen is collected over water, and we're at 22 degrees Celsius, so I know that I have to subtract out the water vapor pressure. And so I'm going to go back and check that chart. I'm going to see it's 19.80 torr. I'm going to say, all right, I've collected this gas, 754 torr. But that is the total gas. It's the what's called the wet, the gas. I'm going to subtract out the water vapor pressure from that table. This is my pressure. And now what I can do is calculate the anything else from it, the volume, the whatever. But I've got to first get that dry gas. So then I could say maybe PV equals nRT. And I could find out how many moles. So I'm going to take that 734.20. Of course, I have to change it into atmospheres, divide by 760 to use PV equals nRT. I have to do that. I have a volume that I collected. I have to change this to Kelvin, and then I'm going to solve for N. So make sure you multiply all of this and divide by this, and try it out on your own and get 0.026 moles. One last thing I want to talk about is Henry's law of solubility. And it's the pressure of the gas above a liquid is increased the more the gas dissolves in the liquid. So you know that we bottle pop or sparkling water under pressure because that pushes the extra carbon dioxide into the liquid, and we get maximum dissolved CO2, maximum bubbly. Another example is divers don't use tanks that contain nitrogen in their scuba tanks because nitrogen, for some reason other than more than anything, dissolves in blood under pressure in deep water. Then if the person surfaces too quickly, it bubbles out of the blood too fast. This is called the bends, and it can be deadly. There's a YouTube video that you can watch there. There is one thing about a tragic display of Henry's Law, and there's a YouTube video. What happened, it was in Cameroon, and carbon dioxide was pushed into the bottom of this lake way, way beneath the ground, a very deep lake. And for some reason, they're not really sure why, but the lake overturned, meaning that the colder, more dense gas at the bottom of the lake came up on the top, and that CO2 was no longer under pressure, came bubbling out of the lake, killing 1,700 people, numerous livestock. And so the YouTube video talks about that more here. This is a decompression chamber that's used if someone is suffering from the bends. You can put someone in there. Also, if they have altitude sickness, I believe that helps as well, but I'm not real sure about that. But this decompression chamber, if somebody goes into that, they can just put the pressure back on the person and then just gradually let up, and they can reverse the effects of the bends. Sometimes they can't completely. So here's an example or some pictures of Lake Nyos, and here's a YouTube video that I would strongly recommend that you watch.